Okay, so problem number 2 for the section 8-2 and 8-3 test review says, in the state of Pennsylvania, 12% of students submit box tops for education to their school. A large school district in Western Pennsylvania runs a contest to see if they can increase participation. So increase participation. I'm already thinking my alternative is probably going to be that the proportion is more than the null value. The superintendent takes a random sample of 210 students, that's important, of course, from the district and finds that 35 have submitted box tops this year. Okay, so I don't actually know my sample proportion, but I can find it by taking the 35 that's submitted divided by the 210 in the sample. Let's go ahead and write that out real quick. That means P hat, my sample proportion is going to be 35 divided by 210. Let's see what that is. 35 divided by 210 is 0.167. Let's round. 0.167 rounding to 3 decimal places. Okay. Do these data provide convincing evidence? That statement. Do these data provide convincing evidence? That tells me that I'm going to be doing a hypothesis test. So that the contest has increased participation, I was right, there's our alternative, in the box tops for education program. Okay, so we need our 4-step process for a hypothesis test for proportions. So I'm gonna, again, look at my IS number 16 notes, but I'm gonna flip to the 4-step process question. Part 2 was about type 1 and 2 errors. Let's get there. Second to last page. Oops, not 2, sorry. Last page, I think, of the notes. No, it is the second to last page. Okay, so this has the big ideas for section 8-3 at the top, and then it gives us a 4-step process problem. So again, I'm thinking I need to state the parameter, statistic, hypotheses, and significance level. I don't actually have to write those words out. I just have to write what they are. So let's label this as our state step. Okay, so my parameter P is equal to the true proportion. I know P is always a true proportion, and in context, it's the true proportion, let's see, of students that submit box tops, right? Of students who submitted box tops. Oh, it does say this year. This year. And notice I specifically have my sample from the district. So my proportion, my population proportion is going to be from the district as well. The district students are my population this year from the district. And the district I'm talking about is this large school district in Western Pennsylvania. Okay, so I've got P, and then I know that P hat, like I said, is 35 over 210. The number who submitted over the 210 and the total sample, which we said rounded to 3 decimal places, was 0.167. I also need to state my hypotheses. So my null hypothesis and my alternative hypothesis. Let's see. I know that my hypothesis is going to be P is equal to something for the null, and then P is in some way not equal to for the alternative. So what is the claim? What's the baseline proportion who submit box tops? Let's see. This is the sample proportion. That's not what I want for the null. I want the baseline. It says in the whole state of Pennsylvania, 12% submit box tops. So I think this is going to be my null value. We want to see if this district's contest increases their participation from the statewide proportion. So I'm going to change that 12% to a decimal. So P is equal to 0.112. That's my baseline. Now again, I want to see if it's increased participation. So that means the proportion would be larger, greater than that baseline of 0.12 for the whole state. Okay, there are my proportions. So now I am ready for my plan step. How do I want to organize this? Oh, I almost forgot something. I need to state my parameter, statistic, hypothesis, and significance level. Don't want to forget that. So it does not tell me a significance level to use. I'm going to use alpha equal to 0.05. Can't hurt. Again, Some of you have asked, why do we choose 0.05? This would be corresponding to a 95% confidence interval. If this is a two-sided test, which I think this is just going to be a one-sided test because it's not equals to, it's just greater than. So this would really correspond to a 90% confidence interval. That's pretty common. Okay, so next step is plan. So remember, I have to write the name of the procedure. For hypothesis test for proportions, it is a one sample, where'd it go? Z test for P. That is what I'm using. One sample Z test for P. Okay, and then I have to check my conditions. So the first condition is always the random condition. And in the problem statement, it says I have a random sample of 210 students. Now, you can abbreviate random sample like I did, RS, but I do want you to put what the random sample is of. All right, that condition is met. The second condition is the 10% condition. So my sample size, remember, was 210. I want to check that that is less than 1/10 of all. Okay, let's remember, what was our population again? It's students from the district. So of all students, and what district? It was a large school district. Okay, so all students in this large school district. So I multiply 10 times 210, I get 2,100. If this is a large school district, there are definitely going to be more than 2,100 students in the whole district. Remember, district is covering kindergarten through seniors. So that is true. Okay. The third condition is my normal condition. And remember, for proportions, we check this by looking at large counts. So instead of doing n times p hat like we did for intervals, we do n times p using the proportion that we're assuming in our null value, so using 0.12. We cannot just use p hat as 0.167 because that's not what's going to happen here. We have to multiply our sample size, 210, times the hypothesized proportion, 0.12. Let's see what we get. In this case, it's 210 times 0.12. It's 25. Okay, so notice in the sample, 35 submitted box tops, but if our population proportion is really the null value, it's really 0.12, then we would have only gotten 25 students submitting box tops. So we can already tell 35 is more than 25. We have some evidence that this has increased participation. We're trying to see if we have convincing evidence. So we have to check n times p is greater than or equal to 5 and also n times q. So let's see, I could do 210 times what, 0.88, but I can also just subtract my number who did submit box tops from the total number. 210 minus 25 would be 185. Okay, so if 25 submitted box tops, then 185 would not have. And that number is also greater than or equal to 5. So that condition is met. All right, all conditions are met. We're ready for the do step. So first things first, we have to write out our general formula, which is the test statistic is equal to the statistic minus the parameter divided by the standard deviation. And then the specific formula is that z is equal to p hat minus p. Remember, our statistic for proportions is p hat. The parameter for proportions is p, divided by that standard deviation, p times q divided by n. And again, p is going to be my null value. So I could go ahead and plug all of that information in. And I think I will go ahead and do that and get my test statistic. So my p hat is 0.167. 0.167 minus p, my hypothesized value of 0.12, divided by the square root of 0.12 times 1 minus 0.12, which would be 0.88, divided by n, which is 210. Okay, remember, if you put parentheses around the numerator, then you can type this in all in one command so that you don't have any rounding error. That is what I strongly suggest you do. Okay, so, oh, you know what? I just thought of before I typed this in. I'm glad I thought of it. I had to round to get 0.167. So I'm going to erase that. And instead of writing this rounded version, I'm actually going to type in my 35 out of 210. And that way I don't have any rounding error. 35 out of 210. Okay, so let's see what that looks like in our calculator. We put parentheses around the top, 35 divided by 210, and then minus our null value of 0.12, end parentheses around the top, then divided by second square root, that null value of 0.12 times 1 minus 0.12, which is 0.88, and divide by the sample size 210. All right, I get 2.08. which since I'm going to use table A2, since this is a z-score, I can just round to 2 decimal places, 2.08. Z is equal to 2.08. Okay, so let's just try that one more time, and I'm going to go back up and select it, and then just come over here to the 35 divided by 210 and replace it with 0.167. Delete out the other, oops. I wanted to leave in the minus. There we go. So delete out the other digits. I have 0.167 minus 0.12. If I had used the rounded number, what would we get? We would round up to 2.10. So that would be a z-score off by 2 hundredths. It's going to give us a pretty different area. So I definitely want to make sure that I'm not getting any rounding error. I'm using the original sample proportion there, the original fraction. Okay, so my test statistic, my z-score is 2.08. That means this sample proportion of 0.167 is 2.08 standard deviations above the null value, 2 standard deviations away from the mean. So let's sketch our picture. Remember that our mean is going to be equal to the null value, 0.12, but we probably want to find sigma sub, not probably, we do want to find the standard deviation sigma sub p hat so that we can label our normal curve accordingly. That's that p times q divided by n. So the square root of 0.12 times 0.88 divided by 210. This is equal to 0.12, sorry, square root of 0.12 times 0.88 divided by 210. I get 0.022. Okay, 3 decimal places is usually good. 0.022. Now, notice if you had used that value 0.022 as your denominator here, you would also have rounding error and it would throw off your test statistic, your z-score. Please don't use the rounded version, type in the whole thing. Okay, let's sketch our picture. So again, we have a normal curve. Okay, we label it in for normal. Its mean is that 0.12, the population proportion, hypothesized value. And then the standard deviation is 0.022, that's what we just found. So we put 0.12 in the middle. We add to 0.12, we add 0.022. to get the first standard deviation above the mean. So that's going to be 0.142. We're going to add that twice more. So plus 0.022 plus 0.022. We get 0.164 and 0.186. 0.164, 0.186. I could also go 3 standard deviations beneath the mean. I'm going to do that real quick. 0.12 minus 0.022 minus 0.022 again, and one more time. So I get 0.098 is my 1 standard deviation beneath the mean. 2 standard deviations beneath the mean is 0.076, and 3 is 0.054. Okay, so we've got our normal curve labeled with 3 standard deviations above and below the mean. Notice our test statistic is 2.08, so our sample proportion should be right about here, just above 2 standard deviations above the mean. And look at that, 2 standard deviations above the mean is 0.164. Our actual sample proportion is 0.167. So it's just above that. And then more extreme, farther from the mean would be to the right, so, or higher. So the area we're actually looking for is the probability that our sample proportion, p hat, is greater than or equal to the value we got, 0.167. And we find that by looking for the probability that our z-score is greater than or equal to the z-score for that sample proportion, 2.08. Now, I haven't been writing this last part in our notes, but I think it might help you make the connection for why we draw this picture with the actual sample proportion and hypothesized mean, but then we use this z-score. It's because those areas are the same to find the actual area. Okay, so let's use table A2, we have a positive z-score, so we're flipping to the positive side. We want a z-score of 2.08. So 2.0, we're going to line up all the way over with 0.08 at the top, 2.08. We get 0.9812. That's our left area. We want a right area. So to find our p-value, we're going to take 1 minus that 0.9812. And let's see, what do we get? Type that into our calculator. 1 minus 0.9812, we get 0.0188. That is our p-value. Okay, notice we also could have used the normal CDF function. I'm just gonna write that in real quick. If I use normal CDF, my left bound is my actual test statistic, so that's the 2.08, and my upper bound is going to be some really big positive number. Oops, I'm not done. Okay, also, again, notice I drew this curve with the population proportion at the center, and then I went up and down by standard deviations. This curve is going to have the same area in the standard normal curve, where the center is 0, and we go up by 1 standard deviation at a time. That has a test or a z-score of 2.08. So that's what I'm filling in here. And then my mean of 0 and 1, again, using the standard normal curve with my z-score. So if I do that, let's see, second distribution, normal CDF, again, my lower is by 2.08. My upper is some large number, mean 0, standard deviation 1, I leave that, paste it in, and I get 0.0188 if I round correctly, which is exactly what I got from table A2. Either way, I put or in here. Okay, so the last part would be to conclude. I kind of ran out of room, so I'm going to move B down here. This is where my B will show up. So ignore that part from now. I need to write my conclusion. So conclude. Let's see, since our p-value, which is equal to 0.0188, is less than alpha equal to 0.05. I notice 0.01 is less than 0.05. Whenever that is true, remember, if the p-value is less than alpha, we reject